Okay, so let's get started on our final unit for the year. So unit 10, we're going to be looking at rational expressions in a bit more detail and talking about graphing. So let's get started with kind of a review of some old things. So let's talk about direct variation first. So with direct variation, what we're really talking about is that if one quantity of one thing goes up, then the quantity of the other thing also goes up. So they're kind of paired and they match. And usually what they do is we write about one varies directly with the other. So example, they could say A varies directly with B. But just because one goes up and the other goes up doesn't mean that they go up at the same rate. So when we go to examine these, we always need to make sure we include a constant. Sometimes it's called a constant of variation. Maybe they'll call it a constant proportionality. But either way, as soon as we look at this sentence, I'm going to break it down. So A varies means I'm going to write A equals, and we have some constant there. Directly with B means that we're going to multiply that constant by B. So A varies directly with B means we'll use the equation A equals KB. Inverse variation means that as one goes up, the other goes down instead. So with inverse variation, we're going to have something very similar. So they could say that A varies inversely with B. So when we go to write a formula involving this, we'll still have A varies, means that we still have A equals K. And then inversely means that we would actually have it as a fraction. So it'd be K over B instead. One key fact when we're talking about inverse variation is that their product, A and B, has to be equal to that K. So an equivalent statement is that their product is the constant of variation. And you can use either one. I tend to think in terms of this, but I'll use this to check. So if someone asks me, is this an example of inverse variation, I'll use this. Whereas most of the time, if I'm solving or just working, I tend to use this. Now, there's a bunch of different variation. We could have multiple things. So let's kind of look at a couple examples where we have several things going on. How about we have A varies jointly with B and C. So jointly means that some things are working together. It could be on top, it could be on bottom, but if it doesn't state one or the other, we're going to go with the assumption that it's going to be direct. So this is again A varies, so we'd have A equals K, and then jointly with B and C, so it'd be K, B, C, all being multiplied. All right, how about X varies jointly with Y and Z, and inversely with W. So again, we have X varies, so I'm going to write X equals K, jointly with Y and Z, so it'd be KYZ, but inversely with W. So I'd have a W on the bottom. So this is just kind of a broad overview of looking at how different things can be put together. Most of this should be familiar for you at this point. Usually I've talked about it a couple different times. So let's kind of look at what problems on, say, the ACT or the SAT or something else as a standardized test that you're going to look at is going to do. So how about we know that A varies inversely with B. We know that when A is 10, B is 2. And they're actually asking us what is A when B equals 5. So these kind of problems are relatively simple. This is one of our basic forms of working with inverse variation. What we're going to do is go through kind of a three-step process every time. First is we need to identify what equation we're going to use. So identify the equation. And that's just a matter of looking at the wording. So we have A varies inversely with B. So again, we have A varies. So I'm going to have A equals K. Inverse with B means it would be over B. So I have A equals K over B. There's the equation I'm going to use. Next, they're usually going to give us some kind of information. And we're going to use that information to find our constant. So in this problem, we have when A is 10, B is equal to 2. So I can actually plug that into our formula to find out what the constant is. So A is 10, B is 2. And now I can solve this and I'd see that K is equal to 20. So now I can use that K is equal to 20 in our overall formula to solve what we have. So our basic formula is A equals 20 over B. And now I can actually plug in the final step. So what is A when B is 5? So we can plug in the B is 5. So we get A equals 20 over 5, which is 4. So this forms our basic kind of steps for approaching these types of problems. Figure out what the equation is just by using the wording. Identify what the constant of variation is. Typically, they're going to give you some kind of starting point that you can work from, and then use that constant of variation in your equation to actually answer the questions that are being asked. Let's look at one more. How about X varies inversely with Y? But instead of them giving something else, maybe they give us a chart, or they give us a graph, or they give us a coordinate point. So however we do it, we look at it and we get some information, like 1080. And then they ask what is Y when X is 100. So here, this is the exact same type of problem. We're going to approach it the exact same way. The difference being is that they're giving us that middle information in some other format. It could be a coordinate point. Maybe they just gave us a chart of X and Y values and you just need to use one. They could give you a section of a graph and you'd have to use it to predict some other section. Either way, we need to get an X and Y because we're going to have to still find the constant of proportionality. So I'm going to go through those same 3 steps. So we have X varies inversely with Y. So there's my X equals K over Y. All right. This time, let's approach it a little bit different. Maybe I want to use the fact that that means that X times Y equals K because that's a little bit more direct. So I know my X is 10, my Y is 80. So we'd get a K value of 800. All right. Now I can use that K value. Oops, that was step 2. Now I can use that K value for step 3 to actually go through and solve the process. So they want to know what is Y when X is 100. So maybe I'll keep using this version in this time. It doesn't matter. You can go back to this one. So we have 100Y is equal to our 800. And I can solve for Y. And I get Y is equal to 8. So it's still those same distinct steps. Come up with the equation. Use the information they give you to find a K. And then find whatever they ask you to find. So that's kind of our first part. It's a little bit of a review, a little bit of new stuff. And now let's go ahead and move on to our last parent graph of the year. So our final parent graph of the year is Y equals 1 over X. So I'm going to go through and do a basic graph for it. We'll talk about how to use it, what to commonly look for. Maybe we'll look at one other example, and that's pretty much it for this warm-up into Unit 10. So if I go through and I graph Y equals 1 over X, we end up with kind of a funny looking graph. Maybe I plot a bunch of points. I'll end up getting points kind of looking like this. I'll end up with points down here. And in fact, we end up with something that looks kind of like this. This is our basic Y equals 1 over X. A couple things of note. One, we actually have 2 asymptotes. We have an asymptote going horizontally right at 0. So here's our Y equals 0. And we have a vertical asymptote as well, coming right down the middle at X equals 0, or the Y axis. So what I'm going to ask you to do is graph a whole bunch of these, just kind of experimenting them, see what you see. But you need to give me domain range, x and y intercepts, and then any asymptotes present. So let's go over that information for the parent graph, and I'll give some tips and tricks to help. So domain, well, it goes left forever, it goes right forever, but it's never actually zero. It's never right there in the middle. So our domain would be all real numbers, except x cannot be zero. We're not allowed to divide by zero, it doesn't work. If I go to look at my range, well, it goes down forever, it goes up forever, but it's never actually zero. It's never right there in the middle. So my range is also all real numbers, except y cannot be equal to zero. On this particular graph, x-intercept, y-intercepts, well, we don't actually have any. Those are actually both asymptotes for this one, so no intercepts. Finally, as we go to look at this, let's talk about the asymptotes. So we have two asymptotes here. We have a horizontal asymptote, and that horizontal asymptote is right here going straight across. So remember, a line going straight across horizontally always has the equation of y equals whatever value it is. So in this case, our horizontal asymptote is y equals 0. Our vertical asymptote is straight up and down here. And again, remember, a straight up and down line has an equation of x equals whatever value it is. So our vertical asymptote is at x equals 0. This forms our basic information for a parent graph. As I ask you to graph them, I'm looking for accuracy in a couple parts. One, you need to mark the asymptotes with a dotted line, mark them nice and clear, have them be accurate. Once you've done that, you only need a couple points on each side, and then try to match the curvature going to the asymptotes. That's all I'm looking for from you on this case. Well, you ask, well, if we have something weirder, how do we get this information? Well, we can actually kind of go back to some of our older tricks. So if instead we were to look at a slightly more generic case of something that looks similar to this, we can actually just look at this and still get a lot of our information. This is the same kind of A, H, and K transformations that we've talked about all year. A is going to give us a vertical stretch or a vertical compression. The signage will flip the whole thing upside down. H is still a horizontal translation. K is still a vertical translation. So in point of fact, the H and the K are what we're really looking for to help graph these. Since H is a horizontal translation, moving the whole thing left and right, H is going to correspond to the asymptote that we need. So our vertical asymptote is actually always going to be x equals h. Our horizontal asymptote is going to correspond to just how far up and down the whole thing is moved. So our horizontal asymptote is just going to correspond to y equals k. So this provides a nice, easy way to get the starting asymptotes relatively easily if we have an equation in this format. So let's kind of look at one quick example here at the end. So let's say that we wanted to graph something like 1 over x minus 3 plus 1. So when I go to graph this and start answering questions, what I'm actually going to do is I'm going to do my basic Cartesian plane, and then I'm going to identify the asymptotes next. So I know I have a horizontal asymptote at k, at 1. So I have an asymptote here at 1. I know I'm going to have an asymptote at x equals 3. 1, 2, 3. So I'm going to have an asymptote here. Now that I have the asymptotes, it becomes much easier to plot points and see the shape. So I could actually plot XY points. You could do an XY chart, however you want to get your points, but we can actually start getting them. And then simply match those points up with the asymptote. If I plotted a few other points to get the other side, we'd have something like this. So there's my basic shape of the graph. I can now start going to my domain. So the domain, it goes left forever, goes right forever, but it's never actually right here at x equals 3. So our domain is all real numbers, excepting x cannot be 3. If I go to look at my range, it goes down forever, goes up forever, but it's never actually right here at 1. So it's all real numbers, excepting y cannot be equal to 1. There's my domain and range. X and y intercept, you can find it however you want. You can use the graphing utilities. We've talked about how to find it on Graphing Calculator. We've talked about how to find it using an online source like Desmos, or you can just solve it normally. X-intercept would be y equals 0, and we can solve it. Y-intercept would be x equals 0, and we could solve it. Again, it's however you want to do this. In this case here, our x-intercept actually comes out nice and neat at 2. Our y-intercept still works out fairly neat. That is at, let's see if I can do this in my head real quick, 3/4. I feel like that's a little bit off. Well, I don't know. Maybe we should actually check. So let's find the y-intercept. So the y-intercept is going to happen when x is equal to 0, right? So if I plug in a 0, that'd be 1 over -3 plus 1. So y would be equal to -1/3 plus 1, which is 2/3. Yep, I was wrong. And we double checked, and it's exactly 2/3. So there would be my y-intercept there. All right, so we have our domain, our range, our x and y-intercept. The last things, we just need the asymptotes, but the asymptotes are fairly easy now because we used them to set up the graph. So my horizontal asymptote was, again, simply y equals k, and in this case, it is y equals 1. My vertical asymptote is, again, just x equals h. H was a +3, so we have x equals 3. So there's my horizontal and my vertical asymptotes. So really, this lesson is just focused on basic review of some solving and using direct and indirect variation, and then just practicing these really basic graphs before we move on to some more complicated stuff next time.